All right, today we're going to talk about the properties of polygons. Now, some of this you've learned back in junior high or even earlier, and some of this is going to be new to you. So you might want to, at least don't just assume that you know everything here. So first off, okay, come on, click. Here we go. A polygon is a closed plane figure formed by three or more non-collinear straight lines that intersect only at their endpoints. So here we have some examples of polygons. Here we have some examples that are not polygons. Again, notice here we've got a curved edge. Here we've got two lines that intersect. So those are not polygons. Now, again, a word that we're familiar with now, vertex, is the common endpoint of two sides. Plural is still vertices. Now, a word that you've heard before, and it means really kind of what you think it means, is diagonal. Although we're going to kind of define it specifically as a segment that connects any two non-consecutive vertices. All right, so if I'm connecting this vertex with this vertex, that's a diagonal. Now, because it has to be non-consecutive, because if I connected these two together, it would just be the side of a triangle, so that wouldn't work. So that's a diagonal. Now, a regular polygon, because again, if you remember back when we talked about triangles, we had equilateral triangles where the sides were all the same, equiangular triangles where the angles were all the same. Well, polygons can work the same way. And so we get kind of tired of having to say equilateral and equiangular, and so we just say regular. If a polygon is both equilateral and equiangular, we say it's regular. So generally we name polygons by the number of their sides. And again, some of these names should be really familiar to you. Some of them you may not have heard before. Specifically, for some reason, people always have a trouble with 7. 7 is heptagon, not septagon. Oop, get back there. 9 should be fairly simple, but again, some people have a little stumble with this. 9 is the only one that starts with an N. So a nonagon is a 9-sided. And then there can be sometimes confusion between the 10 and the 12. Decagon and dodecagon. You might go back to maybe like Spanish 2 is dos, so a dodecagon is 2 plus 10, so you have dos plus decagon. You might try if that works for you. Now, if we're just talking about a polygon in general, like we don't really care how many sides it has, we'll call it an n-gon. That means it could have any number of sides. We don't care. It's just a general polygon. So we want to identify the general name for each polygon. So you get here, you count your sides. You've got 1, 2, 3, 4, 5. So this is a pentagon. Here, again, it's tempting to say it's got 4, but you notice you've got all the little ones here. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 is going to be a dodecagon. And then here we've got 1, 2, 3, 4. So a quadrilateral. Okay. Two other words that you're going to be used to classify triangles are concave and convex. Concave, if you want to think about like what a cave, like if something is caved in, it has kind of a dunk in it. So that's what this we've got here is we have a kind of a dunk in the side of the polygon. All right. Technically, we can draw a diagonal that contains points outside the polygon, but it looks like it has a dip in it. Its side is caved in. It's concave. Convex is basically not concave. So here we have a concave pentagon because I've got 5 sides. Here I have a convex quadrilateral. Now, we all should remember the angles of a triangle add up to 180 degrees, and so we'll see what we can do about the other polygons. So let's say we have a convex polygon that has at least 4 sides. So here we've got a pentagon. And I'm going to go ahead and draw all my possible diagonals from one vertex. And I want to see how many triangles I can make. Well, when I do that, notice here I've got 1, 2, 3 triangles. All right. And so I want to know what's the sum of the angles. Because if I find the sum of the angles, then that will tell me, because again, because this plus this plus this plus this, plus this, plus this, plus that, plus that, plus that is all the sum of the angles together. So if I find, so I've got 3 triangles. 3 triangles is, each one is 180 degrees. 3 times 180 would be 540. Right, yes. Okay, so the sum of the angles of my pentagon here is 540 degrees, which kind of gives us our angle sum theorem for a polygon. Essentially, if I've got n sides, then the sum of the interior angles is going to be n minus 2 times 180. Okay, so we had 5 sides. 5 minus 2 is 3. 3 times 180 was 540. So that's kind of how that works. Now, if my polygon is equiangular, so if all of the angles are the same, then I can find the measure of any one angle by taking the sum and dividing it by the number of sides that I have. Okay. So we've got this chart here. We've got the chart with the names. And so go ahead and I'll start just kind of filling in the number of triangles. Notice here you've got a gap here between 10 and 12. We don't really have 11 listed because it doesn't really have an interesting name. And then you've got the sum of each interior angle, sum of the interior angles, and then the sum of what each interior angle is for a regular one. Okay, so we already did pentagon. So you can do hexagon, heptagon, all those. Okay, so let's go and work on that. And then here's what it should look like when you get done. Okay. To me, the big deal here is you need to know this basic formula right here, because that way, if it doesn't matter how many sides we have, I mean, if you happen to remember off the top of your head that, okay, the sum of the interior angles of a hexagon is 720, yay, that's fine. More importantly to me is that you know this formula. Okay, so it doesn't matter how many sides, you can find what the sum of the interior angles is. And then just use kind of logic to say, well, if they're all the same, then I take that sum divided by how many I've got. Okay. Now that was interior angles. Now let's look at exterior angles. Again, reminding you from triangles, if we extend the side of one of the sides, we form an exterior angle on the outside of the polygon. And the deal with that is that this exterior angle and the angle that is next to have to add up to 180. So let's take the exterior angles of a regular pentagon. Well, I know that each interior angle is 108. I can either find it from my table, I can take, I can use the formula, whatever I want to do with that. So if I know that one of my angles is 108, that means that the exterior angle that's next to that would then be 180 minus 108, which is going to be 72. If that was 72, all the others are 72. And so if I want to know the sum of the exterior angles, that would be 5 times 72, which is going to be 360. Now the really cool, weird, creepy part about all this is that the sum of the exterior angles is always 360. Whether it's any convex polygon, whether it's regular, not regular, no matter how many sides it has, the exterior angles are always going to add up to 360. Interior angles could add up to several thousand degrees, if not more, but exterior is always going to be 360, which I find kind of weird and bizarre. So that is our exterior angle sum theorem, which is the sum of the exterior angles of a convex polygon is 360. And if I wanted to find out what any individual one was, if I had a regular polygon, I take 360 divided by the number of sides. Okay, just like we did with the, you can see how it kind of works the other way going with the pentagon. So finishing our table here, oops, come back. No, anyway, finishing up the table, you can see that each of the individual exterior angles are, and that's it for polygons.